The funny thing is the thing about software engineering is it was actually coined in 1967 by the committee which was running a conference on the same name, software engineering. And the funny thing is, they actually make this name, software engineering, the title for it, to be a little bit provocative, because they reckon already at that time, industry wasn't really relying on anything that has some strong, robust discipline, some rigorous in the industry. They couldn't really find it. And that's why they reckon maybe it would be a good idea if the industry could grab to some disciplines, maybe like math or whatever, to have our software running robustly. Me being functional programmer, I think functional programming as a paradigm is awesome because it brings back all this elegance into our industry back. We get programs which are robust. They are built on rigorous ideas, and the concepts built within help to deal with all the complexity that you can think of within your program. However, functional programming also has issues, even though we have many years of research and we dealt with, dealing with, errors, dealing with changing world and all that. There's still one thing that sucks, and that's recursion. Because if you really think about it, recursion sucks. I mean, you still can have a program that will compile and will not work. It might loop infinitely, it might terminate with an exception, with Stack Overflow, whatever. Those are still things that will give you a compiling program that will basically not work. Obviously, there are some languages, like, for example, like Idris, with its totality checker, which will give you compile time guarantee that this given function, even though it's recursive, it will still work and it will give you a value. But if I ask you a question, who is using Idris on production, probably zero hands. So till we stuck with languages like that, it would be nice to actually have some kind of tool to deal with recursion, which sucks. And this talk is exactly about that tool, which was first, I don't know if it was first described, but this paper is well known. This paper is from 1995, I guess. And this is where they actually describe things which we're going to talk about, which are recursion schemes. So if you'll be interested in this after this presentation to a little bit explore the topic more, this is the starting point. There are many more papers, but this would be considered a foundation for the idea. All right. And also, if you think after this presentation, you might be asking, okay, but can I actually use it? Does it have any real-world application? So just saying, the first link is actually the software that we are writing at Slam Data, which is open source, so you can actually see it's being used. And Matryoshka here is an open source project that we develop as well, which we use in the Quasar project, which is actually recursion schemes implemented in Scala. They are sort of basically a port from Haskell implementation into Scala. Now, if you are not using functional programming at all, or maybe you just use it a little bit, don't worry. You can still write your imperative code base and get a little bit of robustness using recursion schemes as well. Okay, so recursive structures, because this is we're going to focus on recursive structures. What are recursive structures? The simplest example that you can really think of is, for example, lists or the binary tree. So the things that we see today at this conference in the morning. So when list is defined as it's either a null, right, an empty list, or cons. And the way you define a list is in sort of like inductive way, right? But those are very simple data structures. You can think of anything that you use basically in your production. If you have a file system, or if you have a 3D graphical scene or a database, they all, if you think about the structures that you have within your system, a business report, I don't know, whatever, right? A bank report or whatever, they are all defined recursively. So anything that is nested and inductively defined, you can think of it as a recursive structure. So when I was preparing this presentation a few months ago, so I was thinking, oh, I would actually use some real-world example, so you will see the benefit of from recursion schemes. But in the middle of doing that presentation, I realized bringing real-world examples sucks because people were more focused on that example than actually on recursion schemes. So I'm bringing something simple, expressions. Because if you think, so I'm saying that the example is going to be simpler because I want to focus on the topic of this presentation. But the ideas can be used on any arbitrary data structure that you have, even the complex ones. So if you think about expression like this one, you can in Scala represented as recursive data structure, right? So we have a sum, and then we have the tanh, which is squared, and we have multiplication between those two doubles. If, for example, I would like to now take the whole expression and square it, I would just put a square and that whole thing underneath it, and that would represent that expression. Right? Makes sense? So far, so good? Right. So also, we could visualize that expression as sort of a tree. So now we see that recursiveness in the definition, right? So basically, expressions will be the example that we will be working on during this presentation. So this is how we would describe it in Haskell. It's pretty much a definition that we seen a moment ago. So expression can be either an integer or a double, or maybe a sum where sum is taking expression. This is a Scala conference, so we'll be using Scala for examples, and those are a little bit more robust. Boilerplatey. But the thing about coloring your code is actually you can actually focus on the stuff that is really important. So whenever you see anything in colors, I don't know if you actually can see the colors, but believe me, there are colors on those slides. So if you see anything like in grayish, dark color, it's not really that important. Things in color are more important if there's going to be too much code in the presentation. All right. So having this data structure, having this ADT, we could write a function evaluate, which evaluate would be a simple function that would take an expression and give us a value that represents that expression, right? And this is probably the simplest way to write it. So if I have my leaves in my data structure, so either have an integer value with value v, I will just cast it to double, or if I have decimal value, I will just return that v. In any other cases, like for example sum, where I will have to recursively call xp1 and recursively call evaluate on xp2. Once I have those values back from calling this function recursively, I can sum it, or in case of multiply, I can multiply it, or do whatever I'm doing with those values. So, okay, it doesn't really look complicated, right? Like you look at it and it seems fine. Then you will look at the other function, which is called makeString. And makeString was supposed to give you from the expression the string representation of that expression. Now, if we look at it, it looks sort of similar to the function that we have a moment ago. And the reason for that is that we are mixing concerns here, right? One concern is actually evaluating the expression, or creating the string representation of that expression. But the other concern is calling recursively towards the structures that are lying below our current level, which we are dealing with at the moment. So, for example, an example of a multiply, there is the multiplication, the business logic, right? But we also have to do this evaluate here and evaluate here. And those two functions, even they do two different things, the overall template looks exactly the same, right? Because we are doing two different things. We are making a string or evaluating, but we also have to explicitly call recursion. Now, if that isn't a problem, think about something else. Think about a function called optimize. So optimize will take an expression and it will give you an expression back. But the idea is it will optimize your expression. So it will, if it will see that you have multiplication between two expressions and those are exactly the same, it will just give you a square of that expression, right? Which makes sense. So if I have some tree representing multiplication and the left-hand side and right-hand side are exactly the same, so if I were evaluating the original expression, I would have to evaluate the left-hand side, then evaluate the right-hand side, and then multiply. So I'm doing the same things, one after the other. The optimized version would just evaluate this once and multiply by itself. So in theory, it should be faster, right? The problem with this implementation is we're not done, right? This is the core of this function. But remember, there are two concerns here. One is, optimizing. The other one is calling recursively itself to actually evaluate the rest of the structure. So we still have to deal with our rest of our elements within our data structure, right? Even though the only thing that we're doing here is nothing else but just call optimize to the elements that lie below. So this is a very simple example. Imagine anything which is a little bit more complicated. Then your function grows, grows, and grows. And also, there is another issue, right? What happens if I make an error? If I forget to call optimize on XP1, this whole thing will compile, right? It will compile, but it will not work. Most probably, that unit integration or unit test that you've written was probably for this case here. So you won't even realize this thing will happen. This thing will break for multiply, right? What happens if I call, normally for my leaf values, like int value and decimal value, I was just returning the v, right? What happens if I was tired, it was already 10 p.m., I had my 10th coffee, I'm just exhausted, and I just called optimize on it as well, right? This thing will compile as well, but it will not work, and the way it will not work is it will just loop infinitely until it blows up your stack, because it will be just calling itself and itself and so on, even though it compiles. So this kind of sucks, right? Just to give you a general understanding of how the machinery works behind, which is probably you guys already know. So I have some value expression I want to evaluate, this expression here. So I just navigate over that structure. I go to the leaves. The leaves give me back the values. They go back up the structure. Then I can actually call the sum here, or I can call the division here. And at the very end, I go back with the values, and the multiply is being called. The same thing, the same mechanism will work exactly for make string as well. And we see a pattern here. The machinery starts with the root of your structure. It traverses down to the leaves, right? Grabs the value and starts going up, calling your business logic, whatever that business logic is. But it always goes down to the values, grab those values, call your method, your business logic on those values, and goes up calling your method until it reaches one more time the root and give you the final value. Wouldn't it be just nice if we have some machinery that would just do that for us? Let the computer do the traversal over the data structure, grabbing the values from the leaves and going up and calling our method. So our method would no longer work on recursive structures. It would just work on concrete values that we get from the bottom to up. Wouldn't that be nice? Yes? No? You're sleeping? Checking Twitter? Yes. Good, because that's the rest of my presentation. All right, so it would be nice if we had a function like evaluate. It would look exactly like evaluate, but this time here, the expression wouldn't really be expression. It would be just a double. So XP1 and XP2 will be just a double. Double 1 and double 2, which I could just sum. Somebody else would first fetch the values from the bottom, bring them up, so I could just sum it, or multiply it, or square it, or whatever I want to do with it. In case of making string, those XP1 and XP2, those will be strings, right? So, but with the current way I define my expression, I cannot really do it, because right now the expression is just, so those little elements of the ADT which are defined recursively. But I would like to be this to sometimes to be a double, sometimes to be a string, depending of what I'm doing. So we have to do a little trick here. So we have this. We have to actually refactor this to sort of have the ability to write that function we would like to write. And the way for it, the mechanism that we're going to use is making a type. We just introduce a parametricity. So the difference is expression is right now parameterized by A. Whatever the A is, it might be your double, it might be your string. So now the sum, really, sum, which is also parameterized, all those elements are parameterized by A. So now XP1 and XP2s are A's. So if you have a sum of double, you know those two are doubles. If you have sum of strings, you know those two are strings. So this is cool. This is basically what we wanted to have to write this function, right? But now we have an issue, because we made it, it used to be here, this used to be an expression, now it can be anything. But at the end of the day, what I want to have is ability to build a structure created out of those little elements. At the end of the day, I want to have something that is an expression and has expression, and so on. Can I still do it with this representation? This thing, right, this used to be an expression, but now it's arbitrary A, right? It can be any A. It can be double, it can be string. Can it be back an expression? It would be a good idea, right? Just let's say this A is one more time the expression, and this whole thing should kind of work. Well, it doesn't. And so just to give you an example, this is how it used to be. This is how I've defined a simple expression, just a sum of two integers. I want to sum 10 plus 5. That's what I want to represent. And this is what I could do, right? Well, let's try to do it with a new definition of expression. Well, int value has to be parameterized by something. Well, it's not really that bad, because if you look at the definition of int value and decimal value, even though they are parameterized by a's, we don't really use that a in the definition. We just say, int value has int and that decimal value has double. It's not recursive in its nature, the leaves, right? So here we could just put here anything, whatever, user, string. We put unit. We could put unit, we are putting unit, but we could just basically put anything, because that thing inside is completely ignored. So, all right, so this works. What about that? Well, if this thing is now an expression of unit, right, and that thing is also an expression of unit, then we see by definition, if that thing is an expression of unit and that thing is an expression of unit, then this thing can only be what? String. Expression of unit. All right. All right. Good. So if this thing is parameterized by the expression of unit, but sum itself is expression, so the final thing, if it's expression of unit. Holy shit, right? But that's only the simple example. Let's look at something which has like 3 levels. We can do exactly the same thing. We can start with leaves, so we ignore it can be anything, so we put just unit. So we have unit, so this is expression of unit as it used to be before. So now this also has to be an expression of unit. So if those two are expression of unit, then this is parameterized by expression of unit. So the final type is an expression of unit. All right. If you used to be a Java developer, right? You're used to boilerplate, right? You have this ability to sort of deal with that crap around in your business logic. So we could say, we're fine, we're good. We will deal with that, right? Not an issue. But the problem is, what happens if we get a value dynamically? Let's say my input is an expression represented as string, and the from function is a parsing function. It used to parse a string and give me the expression, right? And I don't know, throw exception if it couldn't parse or whatever. How can I represent this right now with my new definition? It used to be depending on how many levels of the structure I have internally in my example that sort of correspond to number of expressions I had in my type. But if I don't know up front on the compilation time what the structure is actually going to look like, what the hell I can do with it? I can have an expression, obviously will not compile, right? So we have to do something about that. And the thing that we're going to use is called a fixed point data type. And not like there are many fixed point data types, but the one we're going to use is the simple one called fix. By the way, how much time do I have left? Okay. Basically? 25 minutes. So it's all right. Okay. So normally at this time of the presentation, like a professional speaker will tell you a joke so your brain can relax. I don't have any jokes. So I will just give you a kitty. Now you can, sort of relax, and I can now introduce a fix, which will blow your mind. But it's not really that complicated. It's only complicated when you look at it for the first time. And then you're good. Okay, so this is fix. Now fix, and your brain is already like, what, right? But if you think about it, it's not really that complicated. So fix, let's try to reason about fix. Fix is just a wrapper. As you can see, it's a class that wraps over some value, okay? So far, so good? It's a wrapper. It will take something, and it just will wrap over it, okay? So what it can wrap over? Well, it can wrap over something of type f of something. We'll see in a moment what the question is, what the hell f is? Well, we parameterize fix by f. So f is some higher kind of type. So it's not really a type yet per se. It's something that will create your type. So it's like a list, right? Or a task or option or whatever. It's not a type. Option of string will be a type. Option is your type constructor here. So it will take something of being a higher kind of type. F is higher kind of type. And the value that you wrap over is parameterized by that f, which is parameterized by fix of f, by this again. And this is weird, I know, but an example should sort of show you that it's not really that scary. So this is our previous example. It's a simple one, right, that we have before we actually introduced paramicity. So let's try to wrap, so the idea here is to wrap everything around fix. And wrapping every element of our data structure around fix, we're sort of remove our problem, sort of. So let's try to do that. Let's one more time try to work from leaves to the root, to the top element of that structure. So the first thing we will do is we will wrap our int value. So we had our int value here, and we wrap it over fix. Okay. Okay. So spoiler alert, f here is going to be our expression, right? So we wrap our int value over fix. So this, if we're wrapping something over fix, that means that value has to be of type f of fix of f. So this thing being an expression of something, so f is our expression, it only, for this to compile, the thing that we will parameterize, that this thing can only be fix of expression. Otherwise, compiler will complain. So if the whole thing, this whole thing here is expression of something, but the question is of what? And this definition here is telling us it has to be parameterized by fix one more time of f. F is our expression, so it has to be fix of expression. All right. So what about sum? Well, let's wrap it one more time. So let's wrap our sum here. Let's wrap it with fix one more time. So now, if we're wrapping fix over expression of fix of expression, then it only means that our type is fix of expression. I know it looks scary, but I have only 20 minutes, so let me continue. With the more complicated example, we will do exactly the same thing. So we will just wrap over our fix. So this will be a fix, and it will be parameterized by fix of expression. And we will do exactly the same thing we did a moment ago. So we wrap our sum with fix, and our decimal value with fix, and our final division with fix. So we get a fix of expression, and every element in the structure is wrapped with fix. So it looks weird, but what it gave us is that we sort of removed that infinite expression of expression of expression of expression till infinity. It's being cut here at this point. So, and the cool thing about Scala compiler is actually you can remove that part. It will be able to infer the type from your definition, and your final definition of your structure, in our example of the expressions, looks like this, which is not ideal, but it's almost close to what we had at the very beginning. At the very beginning, we were defining our expressions this way, right? But now we have to wrap everything around this little fixed element, and the whole thing will compile. What about situations where we were reading something from an input and we don't really know what that is? Well, now it's just a fix of expression, because we cut the infinite fx of x. Having a fix of expression, how I can get the expression back? I don't have any words for this question, but if you look at this, if I have a fix of expression, and I don't want to have a fix of expression, I want to have my expression back. How can I get my expression back? I call unfix, exactly, and that gives me my expression. So I can go back to the expression. So, hooray, we just did what every government around the globe is doing. So we introduced a problem, and after like an hour, we fixed it, right? But there, if you remember, there was a reason why we were doing this. We introduced parametricity to expression so we can write this function in a way that we will not have to deal with recursion. The recursion will be done implicitly for us. So let's try to write it. In order to write it, we need two things. Okay, and one thing is that, so we'll be introducing a mechanism called catamorphism, which is from that paper about bananas and all that. And if you wonder why that it's called bananas, it's because there are many recursion schemes. One of the ones I'm introducing is catamorphism. And a catamorphism in that paper was introduced with an operator which looked like banana. If you know Erik Meijer, the guy with crazy t-shirts, you can imagine why that is. I will not continue because I have a theory why that is. But anyways, so the catamorphism is that mechanism that we are hoping to get. So it's one of those recursion mechanisms, and this one in particular will traverse your data structure to your leaves, grab the values, go back, and call your function with your business logic, right? So that's catamorphism. And it's in that paper, but I don't have time to really go into that. So let's try to focus on real stuff. We need two things. We need that our function we were talking about. We're almost here. We just need one more thing, a functor. Okay, why do we need a functor, and what the hell is a functor? So now, the first question. Don't be shy, people who don't know what a functor is. I will ask one person, and if you don't know the answer, you will do push-ups. All right, everybody know what a functor is. Awesome. That's pretty great. So we need a functor. So I can actually skip that, functor 101, which is awesome. We need to implement a functor for our data structure because the mechanism, the catamorphism that we're going to use just in a minute, have absolutely no idea how our data structure look like, right? We have an expression, could be a bank report, could be a file system, could be whatever. So we need to sort of give them a sort of a notion of how our structure looks like. And the functor will give that for him. So basically, this is implementation of a functor for expression. So just the idea that I have an expression of A, whatever the A is, double string, whatever, I have a function that will go from A to B, I will get an expression of B back. And I hope the definition is pretty straightforward and I don't have to explain. We just basically call those F functions on our A elements, which gives us the B back, and the thing works. All right, since we have that, we can finally have our function. But not really. Okay, no, really. It's going to be our function, but it has a special name. It's called F algebra. And you think already, holy shit, category theory, which kind of is, but we don't really care about it. It's just a name, all right? Just deal with the name. And F algebra is nothing else. F algebra, F of A, is nothing else. It's just a function that goes from F of A to A. From expression double to double. Expression of string to string, okay? It's just a function that goes from FA to A. So in our example, we will define our evaluate function as an algebra expression double, which, as a reminder, is a function expression of double to double. So now we know every element here, every element from the input side, from the parameter, the argument, is the expression of double. So all those A's are doubles. So we can now do what we were supposed to do, just evaluate the value. Multiplication is multiplication. Sum is sum. Squaring is just multiplied to this 1a by itself and all that. So we have just the business logic, right? The same thing goes from make string. Right now, this is an expression of string. So so A is a string. So I already know it's a string. So it shouldn't really be in those quotes at this point. It should be just A1 plus A2, because those two are already strings. So let's focus on evaluate. I have my algebra that will go from expression of double to double. I have my functor, obviously. The instance of the functor for expression is somewhere out there in the explicit scope. And I have some expression here. One of those we've seen before when we were trying to reason about fixed point data type. So now, right now, in order to evaluate expression, I will call the method which is implemented in Matryoshka, the open source library that we see in the link at the beginning of this presentation, which has the catamorphism implemented in it. So it has all those recursion schemes implemented in it. And one of the one we want to use right now is the catamorphism. So the one that will traverse your structure, grab the values, go back, and call your algebra. So we take our expression called kata on it with our algebra, and that gives us a value. We will do the same thing with make string. So it's a different algebra, same example. We call expression to kata on it with make string, and that gives us the string representation for that expression. How is that better from what we had before? A lot of effort to just have that. Well, you have now totality. This thing will not blow your stack. This field will not loop infinitely. It will work because the recursion machinery is behind the wheels and you just doing whatever your business logic was supposed to do. Think about our optimized example. Remember that this part was only the important stuff, and we could do tremendous amount of errors, not only because we have to write all of that just to call recursively our function, but also we could provide errors which would compile but not work. Well, if we have an algebra that would go from expression to a new expression, we only have this. We say what's important, and everything else we just say, well, take the expression and close it over fix. And that's it. And then one more time it works, and you can just believe me, it works. Since I have a little bit of time, think of it. Okay, so how many of you guys think a goto is not a bad example? Not a good thing to have within your language, a goto? Or 2 people. Everybody else is using goto. Awesome. If you read the paper goto consider harmful, the paper, by the way, has 2 pages, so it's worth reading. You will read that, like, what Dijkstra said was that goto is inevitable. You need to have a goto. But it's a good idea to have a goto in a lower level language and have some higher abstraction in your language that you use. So in terms of Scala, in bytecode, one of the codes from the bytecode, it's actually goto. But the abstraction that you get as a developer is while loop, for loop, higher level abstraction. Your code is still, doing a circles, like just jumping around between those different elements within your bytecode. But all that magic, all that machinery is hide, and you don't really get it. 10 minutes. You don't really get it. So you cannot really, destroy your program with it. And the same thing applies here. But if that was really the only thing that we would have from recursion scheme, they wouldn't be that cool. And hopefully you will get within 10 minutes the cool thing about them. Just quickly here, we just saw like catamorphism. It's one of the recursion schemes that you can have and you can use. There's a complete zoo of them. I will just quickly tell you about 2. Just really quickly go through them, and then I will tell you about one more cool feature that you can get from recursion schemes. So anamorphism is sort of like dual for catamorphism. So instead of going with catamorphism, we had an expression and we evaluate to a value. Anamorphism is something else. I have a value, create me the structure, give me the expression. So we could have an example. Let's say I have an integer 28. It is a value integer, and we'd like to have a structure of close over the expression representing it to be like 2 multiplied by 2 multiplied by 7. So what I need is I need, well, with catamorphism, I need an algebra. With anamorphism, I need its dual, which is called co-algebra. And co-algebra is basically the arrow is reversed, right? So I have a value, an integer, a double, whatever, and that will give me a structure. So in terms of this little example that I showed you guys here just a minute ago, the implementation of co-algebra would say, well, if your integer is divisible by 2 and it's not really 2, then return expression, which is a multiplication when one of the elements is 2 and the other element is n divided by 2. And if anything else, like n, just close it with a leaf int value n. So now if I call 12 anamorphism with divisors, it will just give me that representation. I'm not saying, I don't really have time right now to say, why would you use anamorphism in the real world, but there are cases where you would actually use it. And if somebody is interested, I'll actually show you a code base after this presentation. Hylomorphism is nothing else as just calling on some value anamorphism first and then catamorphism. Instead of calling first ana then kata, you could just call hylo. But it's not really just a naming convention for those two operations. The idea is pretty simple. If I were to call ana and kata without hylo, when I would have my value here, then I'm calling ana. So this is doing some stuff. It's creating a structure. It's done, right? It's a one pass here. Then you call kata on it. So now it has to traverse your structure and then go back with evaluating whatever the value is and give you the final value. So we have two passes. First, ana to create the structure, and then kata to go down the structure, go up, and give you a value. Hylo will do those two things at the same time. While anamorphism is, while with co-algebra, you're creating a structure, catamorphism and algebra is already going down the same time. It goes down and goes up. So you have a single pass, and the code is performing a lot better. And you have here an example. So if I have a test where I take some value, whatever value, and I use ana on that value to create an expression that represents like 2 multiplies by 2 multiplies by 2 multiplies by some odd value, and then I call kata on it with evaluate, this should give me exactly the same value. It should give me the n back. So instead of calling those two guys together, I could just call hylo with algebra and co-algebra. Now, you might think, okay, so this is nice, recursion for free, and recursion that works. Is that it? Did I just wasted an hour of my time? If you think about it, it's really cool things that you can do with recursion schemes. And I will just give you one example. The thing is that the product that we're doing is, at least a bit of that product, is a compiler. We compile down from SQL query to a logical plan. And there are many issues when you write compilers. One of them is how you deal with the sugaring. So you have in Scala, right? We have for comprehension, which we know is the sugar to flat map, and with filter and all that, right? So how, if you were writing a Scala compiler, how you could deal with that, and you want to compile your source code, a Scala source code, to a bytecode, right? For example. Well, what do you do with for comprehension? You could do two things. One is called multipassing, and a multipassing is the idea where you will have multiple stages, exactly how Scala is implemented, right? The first stage, for example, could take an existing AST, the source representation of the Scala file, and look for any for comprehension and give you a new AST where all that for comprehension is desugared to calls to flat map, and whatever, right? And then you would have another step which would just do the rest of the work, let's say. Let's just compile everything else to bytecode. So you would have two steps, which is awesome from a maintainability point of view. But because right now you have this little thing that desugars your code base from for comprehensions to a Scala code base without for comprehension. So you can reason about it in a bubble, right? You can write your unit test. You don't really care about anything else. This is going to be dealt in a moment. Later, I'm just doing this. Right? So you can really reason about it. The code is probably robust and it's working, and you can reason about that thing in the bubble as well, like the modularity in pure sense. The problem is it's going to be slower. right? Because you have to go, traverse your structure here just to desugar for comprehensions. And then one more time, traverse your structure here to do other work that you're supposed to be doing while you're compiling that code base. The other approach would be something they called monolith. Not monolith from microservices, and monolith in the term that you have your AST, you have your Scala source code, and you just do everything at once. Which is from sort of like performance point of view, awesome. Because like, you can do all this magic, but maintaining this, it's going to be a horror, right? So now you have to reason, what I want to have, a maintainable code or fast code, and it's a pain, right? Which one should I choose? And now if you think about it, if you have like things like recursion schemes, you could do something which is called nanopassing. So now you can define each of those steps, like for example, the sugaring of for comprehension as a single algebra here. And the other phases as algebras here and here as well. And you can reason about them separately, and you can write your tests separately and all that. But the cool thing about recursion schemes is the fact that they compose. So now you have one recursion scheme that deals with for comprehension, the other one that is doing something else, and the third one is doing something else. And then when you use that on production, you create a final one which is composed out of those three. So you sort of get the best of two worlds. From one side, you have the maintainability. From the other side, the final thing that you get is that monolith one more time. So the composability, ability to bring all those pieces together, it's what really like functional programmers are happy about. Ability to reason in modules, but then summing it up to having something more powerful, something more robust. And that's what recursion schemes will give you also for free. I have like 3 minutes, so I will just skip my sum up. Those are the links I sort of used when I was preparing this presentation. The presentation is online. I will post the link. My name is Paweł Szulc. That's my Twitter account for complaints. That's my email and blog. Thank you very much. I think I have like 2 minutes for questions, so if anyone is interested in asking a question like, why did you waste my time and stuff like that, I'm happy to do it. Yeah.
The big brother is watching.
Hi. Is there a performance impact wrapping everything in fix?
Wrapping everything in a fix isn't. You might think about performance impact because we are on the JVM, so we're calling functions, which are calling functions, we're calling functions. But if you're doing functional programming in Scala, this is already what you have to deal with anyway. So yeah, there might be some performance impacts, but like but at some point the JIT will kick in, and I wouldn't really say there are really that we could say we've seen in our product. We haven't really measured that much, but the question you might have would be what about stack safety, right? So the thing is that everything is tail recursive yet. We sort of the implementation, the Matryoshka that we have is sort of built from the business needs. So so far so good. We didn't have any stacks explosions and whatever. But if they would happen, we'd probably start working on tail recursion as well. If you want to be like very, very popular, you want to have a very, very cool Twitter account, I would recommend writing recursion schemes for any other language other than Scala, because right now recursion schemes are, for whatever reason, very, very popular. So the idea is just take Haskell implementation, implement it in any other language that will support that the type system will be strong enough, and yay, you are popular, and you have like 3,000 followers on Twitter, and
So are you saying you're popular?
I'm definitely not popular because I haven't implemented Matryoshka, but the guys who did, they definitely are.
So, anyone else? Questions, one more question.
I think they have enough. Thank you very much, guys.